Good afternoon, everybody. Thank you for joining us for another session of EI Live for K-12 students and educators, brought to you by the Earth Institute at Columbia University. My name is Cassie, and I'm the Director of the Office of Education and Outreach. And a big part of my job is to bring our scientific research to different audiences. So for those of you who are joining us for the first time, who may not be familiar with the Earth Institute, our core mission is to foster a greater understanding of the science behind sustainability and the climate crisis, and what we as global citizens can do. Experts that make up the Earth Institute include economists, earth scientists, business and policy experts, and specialists in public health and law. The Earth Institute is actually made up of 24 or so research centers and several hundred individuals who collaborate across different disciplines and schools at Columbia University. What we're hoping to do with these EI Live K-12 sessions is to introduce you to some of our interdisciplinary work through our experts. Our June sessions just got announced on Friday, so if you're curious, you can take a look at that on our State of the Planet blog, or just email me directly and I'm happy to share the information with you. We'll be running these sessions on Mondays and Wednesdays from 2 p.m. to 3 p.m. Eastern Standard Time until the end of June, and we'll also have a couple of sessions in the summer planned for K-12 students and teachers. So today we're going to hear from Josh Russell, a PhD candidate at Lamont Doherty Earth Observatory at Columbia. He's going to be leading us through a demonstration of how he uses Python to turn seismic data into a visual story. So this is actually a bit of a continuation of a session that we aired in April. You may remember, if those of you joined us, that one was called The Sound of What's Shaking, where you saw videos and heard sound clips of different earthquake recordings. And so Josh's presentation today will actually take us behind the scenes of how those videos were created. And if you have not seen that session, don't worry, it's not a continuation. This is just kind of the behind the scenes look at how those videos were created. And if you are interested in seeing that, again, please shoot me an email and I'm happy to share the link with you. So just a reminder, we're going to be using the chat box just to the right of the screen where you're seeing this live stream for questions. Josh is going to stop periodically and also ask participants to answer questions, and the chat box can also be used for those purposes. And if you have questions throughout, feel free to type them right into the chat box. I'll be monitoring that throughout the presentation, and we'll make sure that we'll get to your questions. So once Josh is done, we'll get to the questions, but I may also pick and choose a few to ask as he's asking participants to type in answers. If you're not comfortable using the chat box, feel free to also just email me directly. Once the session is done, what we'll do is send a link to everyone who registered for the event through Eventbrite so that you can access the recording later on. We do make the video private for a couple of days once the live stream is over. So as soon as it's over, you won't be able to access it. And then in a couple of days, definitely by midweek this week, we'll send you a link with the final recording and you can access that at any time. So let me know if you're having any technical difficulties. But without further ado, I'll let Josh take over. Josh, go for it.
Thanks, Cassie. Thanks for the introduction. It's really nice to be here and being able to talk to you guys today. So I'm going to be talking a bit about both Python, kind of the programming language and what it is and how we use it in the earth sciences, as well as talk to you guys a little bit about earthquakes. So I'm a seismologist, and I study earthquakes, and not only where earthquakes happen and how they happen, but also how the waves kind of propagate across the earth and what that can tell us about what the subsurface looks like. So I'm going to try and tie kind of those things together, and hopefully there will be kind of an interactive component to this as well. And you guys will actually be able to run some Python code. So let's get started. maybe. Okay, so this is showing, so this has sound. I don't know if people have their speakers on. So this is a video that Genevieve shared about, I guess it was about a month ago now that she did her, her presentation. And this is showing an earthquake that occurred in Japan called the Tohoku earthquake in 2011. It was a magnitude 9.1 earthquake. And this is a simulation that's showing the waves that were emitted from that earthquake. And so you can see, let's see, start it over. You have the earthquake happen and the waves propagate out and bounce off the other side of the earth and come back and propagate back and forth. And so this can happen for a big earthquake like this. These waves will bounce around for months, and it's almost like a bell sort of ringing a bell. And so while we're not going to talk about the sound this time, we are going to talk about how we can sort of use Python to make visualizations not quite as complicated as this, because it takes a lot of, they're kind of complicated, but we will at least kind of dive into the beneath the surface a little bit. And you can see more of these videos like Cassie said in Genevieve's video presentation several weeks ago, and you can also go to the seismicsoundlab.org. So, right. So what is code? So, you know, you may hear about coding or programming, and they both rely on the use of what we call code, which is just a set of instructions that tell your computer how to perform a task. It's basically a recipe that tells your computer how to do a computation or to move files around in your computer. And it's a very flexible, it's a very broad word that kind of encompasses a lot of things. So now what is Python? So Python is a programming language that takes code and translates it into something that your computer can understand. So the very simplest example that people tend to use is shown below, actually, for Python. So print and then hello world, and it prints hello world. Yeah, it's sort of the ground level. It's really just a way to write kind of human language, or basically translate between human language and machine language. So what is coding used for, kind of outside of science? What is it used for in everyday life? Pretty much everything. Phones, video games, any type of transportation relies on programming. Probably your household appliances, Google search engine, and even at kind of a more basic level, you can sort of think of anything that sorts, bins, stacks, separates, that relies on an algorithm as programming or coding. And in the earth sciences, I guess I kind of gave you a little flavor, but we use coding and, for example, Python to transform raw measurements. So what I was showing before were just seismograms, which are ground motion, and transforming that into something that we can actually use to understand the Earth system. So that was what I was showing at the beginning, was using synthetic data. I'm not sure if I actually said that, but it's using a computer model to generate those waves after that earthquake. But this is an example using real data that we measure from seismometers that are actually buried underground. So these are showing, each of these dots is a seismometer deployed across the US. And the colors of these dots are showing the ground motion up and down. So on the bottom, you can see the raw seismograms. These are just showing Is the ground moving up or is the ground moving down? And it's kind of hard to learn anything from those. But if you then take that and transform it into a visual video, for example, you can actually see from this earthquake that happened off the coast of Mexico, you can see the waves actually propagating across the United States. And there's all these complicated things going on as the waves are moving, and that can tell us about what's happening beneath the surface. So here is something we can actually take that data in and produce. So this would be kind of a data product. So it's commonly done in seismology. It's using the exact same techniques that medical imaging use, just like a CAT scan, but we're using seismic waves to do the imaging. And this is showing the velocity, the seismic wave speed of the Earth 90 kilometers down, or around 55 miles down into the Earth. And the different colors are showing you waves that travel faster, and red are colors that are waves that are traveling slower. And you can already see a huge, you can see a lot of interesting things in this map. The biggest one is that everything on the east side of the US is fast or cold, and everything on the west side is slow or hot. And that's because the west side of the US is tectonically active, and there's volcanism and interesting things going on there. So that's kind of a very broad kind of example of that. So some of my learning goals for this session are sort of fall into two regimes. The first one is just the coding aspect. So I would hope that people can leave this session with an appreciation for what Python is and how we sort of use it to transform data into something that we can understand. And I'm also hoping that you'll have a chance to edit and run Python code yourself in your internet browser using trinket.io, which we'll talk about in a little bit. And I would also hope that you guys will take away some science as well. So we're going to talk about plate tectonics and earthquakes and seismology, where earthquakes occur globally and why they occur where they do. The relationships, some relationships between earthquake depth and magnitude, kind of the most simple aspects of earthquakes that we think about. And finally, we will talk a little bit about ground vibrations in New York City and how they've changed due to the COVID-19 lockdown. So we're going to start with global earthquakes. And before we really dive into that, I thought I would show just kind of a broad overview of plate tectonics and kind of the interesting things that are happening in the Earth. So we kind of think of the Earth as being this big rock that we live on, and there's not really a lot going on inside in the middle of it, but there's actually a lot of stuff going on. So we have upwelling at mid-ocean ridges. I can't point with my cursor, but oceanic spreading centers in the middle of the ocean. We have volcanoes in the middle of the oceanic plates. We have oceanic lithosphere that subducts beneath the continents and produces earthquakes. And then that also leads to volcanism on the continents as well, and volcanoes forming. And so there's a lot going on. And one kind of cursor, or one sort of tracer for where a lot of the tectonic activity is coming from, can actually be traced back to earthquakes. So this is showing a global map of earthquakes greater than magnitude 5 for the past 5 years. And you can see that they sort of form patterns and are sort of clustered in particular regions. And you can also see that they vary with depth. So the color is depth here. And we're actually going to dive into this in a little bit more detail. So this is actually, we're actually going to go to this website, and maybe you can try it yourself. Whoops. hopefully it will work for people. But I'm gonna change to it right now. So I'm gonna change my screen. So it's jbrussell.github.io/EILive2020. And there you will find a lot of, a bunch of sort of interactive figures that were made using these visualization libraries in Python, bokeh and holoviews. So I'm just going to do that very quickly. Hopefully this works. Okay, so if you went to the website, you should see, oh, let me move this. So if you go to the website, you should see Earth Institute Live 2020, and you can just click on part 1, and that'll open up a new browser. And this is the thing that I was just showing you guys. Let me zoom in a little bit. So this is an interactive plot, and up here is kind of the toolbar. And right now it has this hover tool selected. So if you hover over an earthquake, it'll tell you some information about it, the latitude, longitude, place, the date, the depth, and the magnitude. But what I'm going to do is sort of switch that off, and then I'm going to turn on this scroll wheel. And so what this allows us to do is to kind of zoom in to the data and sort of see in detail what's going on. So this again is all earthquakes greater than magnitude 5 from 2015 to 2020. And you can start to see kind of interesting things. So for example, off the coast, sort of off the coast of Chile, you start to see earthquakes that are shallow. And then as you go further inland, they start to get deeper. And so these purple ones are very deep. They're about 500 kilometers to 600 kilometers depth, which is what, 350 miles down or so. So that's, you know, from New York to Montreal, for example, down into the earth. So my first, this is kind of my first question point. I'm curious if people can tell me why earthquakes are happening this deep, sort of what these different depth earthquakes can kind of be attributed to. And you can see they aren't happening, for example, in the middle of the oceans. They're all blue, so they're all very shallow. But then once you get towards the edge of the continents, they start to get much deeper beneath the continents. So I'll give you a couple, like a minute or so, or a few seconds, I guess, to type responses if you have any.
Okay, great, Josh. So while we wait for the answers, a question has come up, I believe, about the first video that you, maybe it was the first video you showed. But the question is, do you happen to know the difference between fast and slow earthquakes with respect to the speed of the waves in kilometers an hour, or is there a quantitative measure? I think the viewer was referring to a color scale on a map, didn't have a scale attached to it, so they were just wondering what the unit of measurement was there and differences between fast and slow.
Yeah, so that's a great question. So I think they're probably referring to the map of seismic wave speed with depth beneath. Let me see if I can switch back. Beneath the US. I'm losing my video. But anyway, so that scale, yes, there is a quantitative measure there. I sort of took that away because I didn't want it to kind of be too complicated, but it's usually we talk about kilometers per second. So they travel pretty fast. And the slow to fast there was probably 3.5 to 4 kilometers per second. So that's kind of the ballpark, numbers for that, 3.5 to 4 kilometers per second. Yeah, so they travel pretty fast.
Okay, great, thank you. So we have a couple of answers to the question about why the earthquakes are happening at just much deeper depths within the oceans. Subduction tectonic plates. Subduction is happening much further below the surface. The movement of the oceanic plate sliding under the continental plate, the further inland the oceanic plate moves, the deeper it subducts. And they may be deeper because it's two tectonic plates, I guess, butting against one another. So those are a couple of the answers that we got.
Okay, those are perfect. That's right on. That's exactly what we're seeing. So you can notice the purple dots, which, yeah, we'll get into this in more detail with some other tools, but you can see the purple dots are really lining the Pacific plate, and that's kind of the ring of fire. And so the Pacific plate is made of oceanic lithosphere, and it's much denser than the continental lithosphere, for example, in South America. And so the dense oceanic lithosphere will tend to dive down beneath the more buoyant continental lithosphere. And so you can see this happens in a lot of places. The Tonga Trench, this one's really beautiful. And a couple of other places you may hear about big earthquakes, and Indonesia, in Japan as well. So yeah, that's kind of the broad scale thing that's going on. So I am going to go to the next one. So yeah, so that's actually quite a bit of data in this one figure, and it's only 5 years worth of earthquake data, but the catalogs stretch back much further than that. They can, so I was able to, stretch back and pull data from 45 years ago. Oops. So this is actually the one we want. Yep. So from 45 years ago, and you can see that, yeah, so that would be way too much data to put into your web browser. And it's I think more than 50,000 earthquakes. So some of the strategies we use to deal with bigger data sets and visualize them is, for example, this, which is called a data shader in the Bokeh toolbox. And so it actually takes all those earthquakes and bends them into these little pixel, sort of counts up all the earthquakes that occur within a pixel, and then maps those to a color. So all the black parts on the map are count 0, so there are no earthquakes there. But if you go to kind of the white and red parts, that starts to show you where the earthquakes are happening. And this is I just thought this was a really cool map to show kind of where the plate boundaries are, because you can see it's really, it also shows really interestingly, there are these really sharp plate boundaries that tend to happen on the edges of the oceans. But then once you get into the continents, you'll have these really broad plate boundaries where you have a continent smashing into another continent. So that would be India kind of plowing its way into Eurasia and creating this sort of cloud of earthquakes. So I thought that was kind of cool. So we will jump back to the keynote presentation, I think. Right, so we will move on to a more kind of interactive part. That is not where I wanted it. Okay, so right, you guys already got it. So as you subduct oceanic plate beneath the continents, you get earthquakes happening deeper. And interestingly, the really big earthquakes, like the Tohoku earthquake I showed in the first slide, this sort of video, happens pretty shallow usually. And the reason the Tohoku earthquake was so destructive was because it actually, the fault actually ruptured all the way up to the plate interface where all the way up to the trench where the plate first starts going down beneath the continent. Okay. So we're gonna try to make your own earthquake map. We'll see how this goes. So we're gonna do this by using something called Trinket. And these trinkets you can open in your web browser and can actually run Python code in your web browser. So you guys won't have to download anything. And the way that these work is sort of on the left side, you have this window where you can type, and this is where the code goes. And the structure of Python codes, sort of the way I've set these trinkets up is there are these variables in these boxes called make changes here. So you can edit F, for example, and A. We'll talk about what that is in a second. And then you run the code, click the triangle, and then it'll output a window with the output from your code. So let's see, crash course. So yeah, so we're gonna start with a really basic example for waves. And I'm sure a lot of people are familiar with sine waves. And so this is just showing kind of a schematic of that. You've got time, or x in this example, on the horizontal axis, and the amplitude on the y-axis. And so this is just sort of a schematic showing you different things. The thing we're gonna play with is frequency and amplitude. So amplitude is the height of the wave, and the frequency is related to the wavelength. So a wavelength is measured from a peak of one point on the sine wave to a peak on the next point on the sine wave. And frequency is related to that. It's proportional to 1 over the wavelength, or vice versa. So as you increase frequency, you decrease the wavelength, for example. So we are gonna try actually doing that. So if you go over now to, let's see, sorry. So if you go over to make your own maps on the side, you will see, hopefully you will see this page. And what we're gonna do is we're gonna play with this trinket, which is right here. And so if you run this, hopefully this will work for people, because yeah, let's see. Okay, here we go. So you can sort of make the window bigger or smaller like this. You can also open it in another page. So what I just did was ran this code where you sort of build the sine wave like I had just shown in the previous slide we were looking at, and then it basically plots it. So you don't need to know too much about what everything is doing down here, but I just wanted you to play with and kind of get a feel for changing the frequency, for example. So let's change it to 5 and see what comes out. So you can see there are way more wave cycles in this range. What happens if we do 20? You should have 20 times more. And then you can play with the height. So this is a height of 1, but you can get 10. You can make it whatever you want. And so I hope that this will actually work for people. And this is kind of just a toy to test out in a really simple way, kind of how Python code runs. And you can change it, you can break it. Breaking code is always a good way of learning how it works. So there we go with that. And so in the next part, I actually want to read in some of those earthquakes that we looked at the first time, sorry, on the previous demonstration, and plot earthquakes that fall within a certain depth range. So you can define a minimum depth earthquake and a maximum depth earthquake. And you can also define a minimum magnitude and a maximum magnitude. So this is a little less stable testing it out than the other one. So let's see if it runs. We're throwing a lot of data into this trinket. So I think it's having a bit of a, yeah, it was having a bit of trouble earlier. So sometimes if it's not plotting, you can click on this triangle and click console, and it'll actually show you what it's doing. So I was hoping it would, let's try again. Let me try resetting it. One more try. So I was having some luck with it earlier, but every once in a while it got a little bit angry because I was putting in too many, I think probably because I'm trying to load in too many earthquakes. So let's try with a smaller magnitude. Maybe that'll work. So I tried with a smaller magnitude, so there are a few less earthquakes. So right now it's showing only 13. So these are kind of intermediate magnitude earthquakes with larger magnitude. So I was really hoping, yeah, hopefully you guys will be able to play with this a little bit. So what I wanted to ask was, yeah, so let's try something like this. Small magnitude, so shallow, relatively shallow earthquakes and only magnitude 5 to 6. So I was hoping that you guys would be able to play with this a little bit and I could ask you some questions about where the deep earthquakes tend to focus and where the shallow earthquakes tend to focus, and also where the larger magnitude earthquakes tend to focus. But maybe you can play with this a little on your own later. And yeah, hopefully it'll work better than it is right now. It might also be the fact that a bunch of people are trying to use it all at once. So it's all kind of in the same, running off the same server. So anyway, we actually have a much better way of getting at where different earthquakes separate out on the next section. So this was kind of just an exercise to get you familiar with how you kind of plot stuff and change stuff in Python. Yeah, so so if anybody's up for the challenge, if they can get it working, I was gonna propose this challenge of actually putting a latitude and longitude filter on this as well. So right now it's minimum depth, maximum depth, and minimum magnitude, maximum magnitude, but it doesn't, there's no filter for where earthquakes happen on the map. So, or yeah, where earthquakes are on the map. So that would be a challenge to you if you can do that. So we're actually going to jump to this next part, which I think is a little bit easier to digest. So now we're looking at the same data set again. Oh, and I should mention, for anybody who's interested, all of these figures have this view code button. And if you click that, that'll show you kind of under the hood all the code that went into these interactive plots. So this one is pretty cool because it allows you to sort of link data together in multiple plots or multiple figures. So this is showing, again, seismicity. I'm going to turn off that. So it's showing seismicity globally. And the cool thing with this one is that you can actually now, for example, in South America, oops, you can enable this box select, and then you can actually select points in the box and see where they land on this depth magnitude plot. So this is showing all these earthquakes, I think something like 8,000 earthquakes. And for each of those earthquakes, it's showing you the depth that it happened and the magnitude. So you can start to see some really interesting patterns kind of emerging looking at the data in this way. And so I actually just wanted to ask what patterns people, even just looking at this map without linking the data together, what patterns people are kind of seeing in this depth magnitude plot. And in particular, do you think does it look like there are more or less, are there more small magnitude or large magnitude earthquakes? And where do you think these, well, we already talked about it, where are the deeper magnitude earthquakes happening?
Okay, great. While we're waiting for people to chime in on that, we have a question about why would you, how is Python preferred over other programming languages or other software? You know, last week we had someone show us maps with GIS and ArcGIS specifically. So can you talk about why, you know, for yourself, why Python is perhaps your programming language of choice?
Yeah, so there are lots of programming languages, and everybody, people tend to kind of gravitate towards their favorite ones. So for mapping, a lot of people use ArcGIS because you can make really pretty maps with it. I'm not as familiar with that. But the nice thing about Python, in my view, is that number one, it's free, and so anybody can download it. And there are all these libraries, is what people call them, that you can install on your computer and use, like these visualization libraries that I have here. So it's probably possible that you could do the similar thing with ArcGIS, for example. But I think Python is a lot more flexible in what it can do. It's not just focused on maps, but it can do maps as well. So that's, I think, the short answer.
Okay, great. And we have an answer kind of about the earthquake magnitude versus depth plot there. One of our participants has said that there seem to be fewer earthquakes in the 300 to 400 depth range.
Yep.
Okay, very great.
Yeah.
And if anyone else has observations, please chime in and add it to the chat box.
Yeah, that's a great observation. And that is kind of an enigma in a lot of ways in seismology. Why is there this depth range where there are fewer earthquakes? And one of the thoughts is that, so you can see at the shallow depths, you have a lot more earthquakes, and a lot sort of larger magnitude ones as well. And then as you go deeper and deeper into the earth, one thought is that because the temperature is increasing as you go deeper, you're actually turning brittle stuff that breaks really easily, like in an earthquake, you're sort of warming that up and making it mushier, and so you're less likely to get earthquakes as you go deeper. And then you reach this point where there aren't very many earthquakes happening at all, and then something interesting happens deeper. And that something interesting that happens deeper is still a research question. And some of the theories are that one is that there's a phase change in the rocks as they're going down, because you're compressing and heating up the rocks so much, they actually turn into their crystal structure actually changes into something else. And that something else can host earthquakes. And so that's kind of I think probably the favored explanation for these deeper ones that aren't necessarily supposed to happen. Yeah, so you can sort of I urge you to sort of play around with these, with this map. It's really fun. You can, for example, selecting all the deep earthquakes kind of shows us what we had seen before, where all the sort of purple ones line up. If you choose shallow, you just get earthquakes everywhere, pretty much. And selecting stuff from the map, if you select, all this stuff in the ocean, all the mid-ocean ridges, you get all very shallow earthquakes, because those are all happening near the surface, near the seafloor. So yeah, I would say I would urge you to kind of explore this a bit more. And again, email questions if you have them. So I will go very quickly over this because I want to leave even more time for questions at the end, and I want to spend a bit of time on the seismic noise part because it's, I think, pretty cool. And so one of the things from this exercise that you might be wondering is what kind of determines magnitude, and why is the magnitude kind of distributed the way it is? Is it just completely random, the way that the magnitudes are distributed, or is there some rhyme and reason for why there are much fewer magnitude 8s, for example, compared to magnitude 5s? And so because people are very interested in magnitude, because it has a lot of impact on society, you know, large magnitude earthquakes are the dangerous ones. People have spent a lot of time for a long time studying earthquake magnitude. So we're going to talk very quickly about what's known as the Gutenberg-Richter relation, which is one of the most important equations in seismology. And it's relating the number of earthquakes that happen of a given magnitude to that magnitude. So I'm gonna just skip straight to the data. And so what this is showing is for all the data on the previous plot we were just looking at, this is showing, let me select these. So for example, the dots are showing the number of earthquakes greater than that magnitude. So for example, the magnitude 5.5, there are 1,744 earthquakes greater than that magnitude. And for example, 6.5, there are 172 earthquakes greater than magnitude 6.5. So as you go, basically, as you go to a higher and higher magnitude, you have fewer and fewer earthquakes of magnitudes greater than that. And the really cool thing is the red line, which is the Gutenberg-Richter relation. So that is this equation plotted on top of the data. And you can see that it matches the data really well. And it's a really simple relation, yet it can explain the data pretty well. It just so happens that at least at the global scale, for example, a magnitude 7, 52 earthquakes greater than that, is about, so for every magnitude 7, there's about 100 magnitude 5 or greater. Or let's look at magnitude 7 and 6. So magnitude 7, there are 52 earthquakes greater than magnitude 7. For magnitude 6, there are 500. So it's a factor of 10. It's logarithmic. So as you increase in magnitude, you decrease the number of events that happen by a factor of 10. If that makes sense. So I am actually going to jump. Yeah, so if you have questions about this, definitely put them in the chat, and maybe we can answer them at the end. So next, I wanted to jump to seismic noise, and to do that, I want to talk about, or I want to switch back to the presentation. So I wanted to talk very quickly about what a seismogram is, because that's the data that's actually going into what we're going to look at next. And so playing this video, an earthquake happened here, the star is an earthquake, and all these colors are waves that are traveling from that earthquake. And up in the top is a seismogram that's being written out at this station, this triangle, over time. So I'll play it again. And you can see the first arriving, so right now there's nothing being written on the seismogram. And then when the first arriving wave hits the station, you get this little spike, and then you get all the stuff coming afterwards. So that's just measuring the ground motion at the station. And I think Genevieve showed this video as well in her session. So it turns out that seismometers not only, somehow the text didn't get included. So seismometers measure ground motion, but they don't only measure earthquakes. They measure all the other stuff that's going on around them. So this little schematic is from a paper that was studying how elephants communicate through stomping their feet. And so below the man and the elephant are actual data from a man jumping, I think, a kilometer away or something, and an elephant walking a kilometer away from the seismometer. And so, as you might imagine, yes, seismometers that are in really busy places like New York City pick up a lot of things that are not related to earthquakes. And it turns out there is a seismometer in Central Park, and it's near, I think, 97th Street that cuts across the northern part of Central Park. And what I've done is, go back to the website. So what we've done is taken that data and every hour measured the average ground displacement of the seismogram. So it just looks like noise, but for every day you can take kind of the average vibration for every hour of the day and then just plot that. And so on the y-axis is the average ground displacement in nanometers. So they're very sensitive instruments. And then on the x-axis is date. And this, I think, goes to the 13th maybe or 15th of May and starts on the 9th of February. And so there are these tools. Now we're going to use the scroll wheel. So you can scroll in X and Y. And there's a lot of interesting stuff on this plot. And that's why I wanted to spend a lot of time on it. I guess we don't have that much time left, but these lines are marking kind of particular events. So this one here is the first COVID-19 fatality in New York. This dotted line is the stay-at-home order. And this other dotted line further over is the subway closing overnight. And you can see there's a really clear change in the noise over time as people are sort of staying home more often after the stay-at-home order. So if we zoom in, let's kind of look at what it looks like before. So there are these really clear peaks in time. And I wanted to ask people, what do they think these troughs and peaks are? So I should mention the really jagged line is the hourly average, and the blue thicker line is the daily average. So you can see the daily average is much smoother because it's averaging out the hourly average. But yeah, so maybe we can pause for a second to see what people think these are. And just to give you a little more context as you are maybe typing, you can mouse over the points. So this is 8:30 a.m., 8:30 a.m. This one's a little different. There's one at 8:30 and one at 10:30. This is 7:30 a.m. So there's a little bit of variability, but 7:30 to 8:30 is kind of the peak. And then down at the bottom is 2:30 a.m. and 2:30 a.m., 3:30 a.m. So maybe that'll give you a little bit of a hint.
Great, thanks, Josh. So it's funny, the seismographs kind of measuring all kinds of things reminds me of a story. I'm not sure if you heard this, when Lamont was first started, it was actually a group of seismologists who were working on the Morningside campus, and that the seismographs that they had were actually they kept getting interference from the subway movement around 116th Street at the 1 train. And so it was from that they convinced Columbia to actually move their that whole group out to where the Lamont campus is now. And for our viewers, Lamont is in Palisades, New York, just a little bit north of the New York-New Jersey border. So we have to go through New Jersey to get to back up to Lamont. But it's makes for an interesting story that the seismographs were picking up all the subway movements.
Yeah.
And that was interfering with the work of the scientists. So I always find that super interesting. That we had a couple of questions. So I'm going to ask the one that I think was related to the Gutenberg-Richter kind of equation that you showed.
Okay.
So does that, so the question is, does the Gutenberg-Richter relation have any predictive power? Do they use it to guess how many earthquakes of a certain magnitude we should expect in a given year?
So that's a really great question. It doesn't, yeah, so I guess first sort of the word prediction always kind of scares, always kind of scares seismologists a little bit because, yeah, it's really hard to predict, especially where and when an earthquake are going to happen. But I would say that it does have some predictive power, or maybe forecasting power is a better word.
Okay.
But yeah, so for example, if you took a year's worth of data, so I did that with 5 years worth of data. So it's kind of telling you how many earthquakes are occurring within, 5 years. If you were to take a kind of a year's worth and look at that, then maybe you could say something about, for a given amount of time, how many magnitude 7 or greater would you expect to see? It doesn't necessarily tell you the magnitude of the earthquake that you're expected to see, because it's sort of that that y-axis that is for like a magnitude m and greater. So you can only say like there's a chance of 50 magnitude 6 and greater in a year or something like that. Maybe I shouldn't say that without actually knowing the number. But yeah.
No, that answers the
That's
question.
a great question. Yep.
Yeah, it is a great question. I'm going to sneak in one more question before we go to some of the answers. So you were talking about ground motion. I think when you were talking about the stomping elephant and the human being.
Yep.
And so by ground, this is a clarifying question. By ground motion, do you mean the movement of sound through the ground, or how the sound moves the ground?
Yeah, so kind of both.
Okay.
So it's the thing that the seismometer is actually measuring is the wave that was produced from the stomping elephant, for example. And you can think of that wave as like a sound wave that's traveling through the earth. It's not exactly perfectly correct, but yeah, you can sort of think of it like the seismometer is an ear, and it's just hearing whatever is whatever's going on around it.
Okay.
If that makes sense.
Yeah. Great, thanks. So the consensus in amongst the viewers seems to be that it's rush hour versus the evenings, and perhaps the 5-day work week versus the weekends are the peaks and dips in the plot.
Yep, that's exactly right. So yeah, you can really, yep. Is there another?
No, that's it.
Oh, okay. Yep, that is correct. And it's kind of amazing to me, when I first looked at this, it's totally amazing to me that it's such a repeatable pattern. And Central Park is the perfect place to look for that, because you're kind of in the heart of New York City. So yeah, a couple of interesting things about the data in the plot. So you could see that shortly after the first fatality, you start to see a drop in noise already, not a huge one, but you sort of start to see it. And then by the time I'll put this back up, by the time the stay-at-home order happened, you get another slight drop, and then the week following that, there's a big drop. So it took people a little bit of time based on this to actually react to the stay-at-home order, it sort of looks like. And the other kind of interesting thing, maybe scary thing a little bit, is that you can see it if we zoom y-axis a little bit, but you can see it's actually starting to, let me turn these off. It's actually starting to ramp back up a little bit. And I think that's people, the weather getting nice and people want to get outside, especially, the seismometers in Central Park. So it's definitely going to pick up a lot of people walking around and stuff. And so I thought that was kind of interesting that it actually looks like people are getting out a little more lately. So be careful out there, I guess. And let's see. One other interesting thing that just happened. So they actually closed the subways from, I think it's 1 a.m. to 5 a.m. starting a few days ago, week ago maybe. And that's this line here, this dotted line. And you can see immediately after that happened, the noise, so it doesn't affect the daytime noise very much, but it affected the nighttime noise a lot. Maybe a lot's not the right word, but it affected the nighttime noise for sure. Where before the subway was shut down, it was less noisy, and now that the subway's shut down, it's more noisy. And my thought is that it could be because people are just using the park. It's right next to 97th Street, and so people are probably taking Ubers across Central Park now instead of taking the subway late at night, or walking, maybe, hopefully not walking that late. But yeah, so I thought that was pretty interesting. There is a lot to talk about in this single plot. I don't know if I think I probably don't have time to talk about the next part, but just so you know it's there. There is, you can actually try making your own noise plot. So all the data from the plot above that is contained in this trinket, and the thing that you can play with now is the running average. So that thick blue line in this figure is a daily average. So right now it's set up to reproduce that 24-hour average, but you can play with that and see how the noise kind of changes with different time windows. And hopefully that will work better than the last one. And we definitely don't have time to talk about it, but I'll just leave it here and you guys can look at it yourselves. But I've also taken the electricity data, some open electricity data for hourly load in New York City, and plotted that together with the daily noise. And so you can click this. It's a little busy, the plot, so you can actually click the legend to remove stuff. But you can see it follows a very similar pattern to the seismic noise, and that's they're not directly linked. The noise is not due to electricity usage, but they're both linked to people. And so with the businesses shutting down and things like that in the city, the electricity consumption has gone down, and just like the seismic noise has. So that's kind of an interesting correlation. And I think that is all the time.
No worries. We can go a couple of minutes over, because this is fantastic. I think representation and just visualizing data, because for our ArcGIS session last week, one of the maps that participants worked with was actually New York City noise levels, but using cool. It's interesting how everybody kind of gravitated towards this. Yeah. Noise levels in New York City, because I'm sure there are a lot of interesting things to look at, but this is a great kind of example of the different ways that scientists can use data, and they can visualize it differently, and you can explore different things. The ArcGIS map was looking at the 5 boroughs and looking at the number of 311 complaints across the boroughs, and then through the ArcGIS map, yeah, and then you could look at which specific neighborhoods within each borough got the most 311 complaints, and then even with at a more detailed level, looking at what kinds of the complaints were. So was it from sort of parties and loud noise? Was it from before or after hour construction? So that's an interesting breakdown. And then this is showing us a similar topic, but a completely different representation. So I think it's a great example, and I encourage everyone who's watching to explore this a little bit more on your own time. We have 2 questions right now. And the first question was, what technique or instrument is used to measure the depth of earthquakes?
Yeah, that's a great question. So the seismometers that, right, let me go back to the video. So this data, for example, from an earthquake that's being picked up on a seismometer, even on the other side of the world, can be used to locate where the earthquake is. So you have to have, it's helpful if you have a bunch of seismometers all scattered all over the earth that can record the wave. But then if you take kind of the simplest thing is to look at the first arriving wave, so the P wave, and then use what we know about the velocity structure of the interior of the earth, like I showed the seismic tomography, use that information to actually figure out, based on how long it took the wave to get there, where did it come from? And so that'll get both the location and the depth of the earthquake. The depth is a little harder than the latitude, longitude, but it's, yeah, that's pretty much how it's done.
Okay, great. And the last question we have is, can students, is there a DIY seismometer kit or seismograph kit that students can play around with that would allow them to monitor seismic noise from home? This is from an educator who has students at home needing to get involved with an activity.
Yeah, that's great. So there are definitely, so kind of the most basic seismometer that you can get your hands on is actually just your phone. So there are seismometer apps you can download, and you lay your phone down flat on a table, and if you knock your knuckle on the table, you can see it show up. And actually, they're starting to use this technology in LA to provide data to seismologists that can be used for an early warning system. But to kind of more directly answer your question, there are the iris. So I'll put I have some websites on the resources link at the bottom of this tutorial. And one of the places to look is iris.edu. So this is showing a link to the ground motion visualization I showed earlier, but they have, I believe they have a link where you can actually choose a station and see sort of real-time data from that station. Would it be useful? Yeah, I can put that link on this page if that's useful, or the person could email me or Cassie and I could provide that link to you.
Great. Yeah. And the last thing I'm going to ask you is if you could talk a little bit about part 2 of what you're going to do on Wednesday. For those who may not be signed up for Wednesday, we have different people participating today and Wednesday. So if you could give us a sneak preview, that'd be great.
Yeah. So part 2 will focus on sound. So the first video I showed in the slide presentation was of, I'll just go back to it, was of wave propagation in the earth, and the sounds that are being produced by that are actually directly sonified from seismograms. And so I'm gonna hopefully take you guys through how we actually can do that and how you can input data into Python and actually pull sound out, because as humans, we're sort of hardwired to pull patterns out both visually and with sound. And so combining those two things together is a really powerful way to kind of grasp really complicated data sets.
Great. Okay. Thank you so much. And I've just shared the RSVP link for Wednesday's event in the chat box. So if you haven't registered, please do. And what a similar thing will happen just like today, where I'll send out a YouTube link about 30 minutes before we get started. And then you can join us for the live stream. So thank you, Josh. That was awesome. And really, really great overview of Python and the different kinds of things you can do with it. For those of you who have any additional questions you might not have had a chance to get answered today, please email me directly and I'll be happy to pass that along to Josh. We'll resend the link as well as a recording to this video later this week. And we hope to see you back on Wednesday for part 2. So Josh, thank you so much again. And everybody have a great rest of your day. And Josh has just shared the link to the Seismic Sound Lab. So do you want to say something about that quickly?
Sure. It's probably also in Genevieve's session, but it's if you're interested in seeing more videos, sort of using sound and visualization together, the seismicsoundlab.org has a bunch of them, and there are a lot of the videos that Genevieve shared in her presentation a few weeks ago, but also additional videos. So I'll just leave it at that. Yep.
Okay, great. Awesome. Well, thank you. And we'll see you on Wednesday.